Thank you. I am super grateful that there are just like this that there are just like this many people who want to like be awake and like at a talk at 9 in the morning for me. Thank you. I was talking about joint work with my grad student Bunrang Zhang, who is not here, I notice, but she's here for the semester, but I think that she chose to like sleep in. It's fine. I'm sure that she's seen this work before, and it's also joint work with Sarah Crable, who is at Richmond, and two folks who are like in my department, Yajia Mei and Ray Tuo, who just moved to the University of Texas. So the change point problem is one in which you have like a stream of data, and you want to like identify some times at which these data change in like a structural way. And so at first we're going to say the first k star points are sampled from some pre-change distribution p0, and then at time k star we're going to assume that things change in some other post-change distribution p1, and you don't know the change point time k star, and so that's the goal is to find this time k star. And we're going to assume p0 and p1 are both perfectly known, and that these points are being sampled by ID. If you don't like those assumptions, wait until my very last slide. But until then, these things are going to hold. What do we care? Maybe we want to like collect like hospital data and see at what point are we starting to see like dramatically more cases of a like particular disease, and so the CDC might want to be doing this. You also might have some like smart home devices who want to test, are you home or not? Is there like activity in the home? And for both of these cases, these are like highly sensitive data, and so we might care about doing this privately. I think for this audience, I'm gonna not really say too much about the definition of like DP. If you don't know it, what have you been doing all week? And so we're going to use differential privacy. And the goal is we're going to want to output some like a private estimate of the change point time that is differentially private with respect to changing one single point in our data stream. So, any questions before I say more? Cool. All right, so here is an outline of both the talk and the paper. So we're first going to talk about this offline case. How do we handle this if you have like all of your data known up front and you want to look back and say like at what time do I think a change occurred in the past tense? And we'll then talk about the like online case if you receive one single data point at a time. How can you quickly raise a flag when you think a like change point occurred? And like in the paper, we have some like empirical results, but I figure for a theory crowd, I don't know if you guys care. Okay, so let's talk first about this offline case. So first, before we talk about privacy, this is actually a very well studied problem in the like statistics case, and they use the like cumulative sum algorithm that came from back in the 50s. And it takes in some like input database X, and it's going to compute a log likelihood ratio for each possible point in time. And it's going to ask, at time k, how likely do I think a change occurred at this time? And so that's going to be our like log likelihood. And really it's going to be so really we're going to say I'm going to sum over all time how likely it was probability of seeing the data, of seeing xi under the alternative hypothesis over the probability of seeing xi under the null. But until time k minus 1, this ratio is actually the same because they both say they're going to be sampled from p0 for the first k minus 1 times. And so that's why it reduces the sum actually starting at time k. And so that is our, yeah?
I'm sorry, quick question. There's only, we know that there's only one change.
Yeah.
It's just a matter of when it happens.
Yeah.
Not how many changes or multiple changes. It's
For now, yes, we're going to talk about multiple change points at the end, but kind of until I tell you otherwise, it's only one.
What's the null hypothesis? No change?
No change. Yeah. Yeah. And so the null is that things are sampled from p0 every time, and the alternative is that they were sampled from p0 up until k, at which point things change to being sampled from p1.
So we assume that n is known, like the time horizon?
Yes. Yeah. Yeah. And because here we're still in the offline case, you see the entire data set up front. And so then in the absence of privacy, we just compute MLE, which is basically the time k at which it was the most likely that a change occurred.
Do you assume the change only happens once within the n sequence?
Yes, yes. And that was the same question about multiple changes. We will see that at the very end, but for most of the talk is just one change. And then you say that a change occurred if we had likelihood above some appropriately chosen threshold based upon P0 and P1 and N. And so that's how you handle things if you don't care about privacy. And really, we only touch the data through this step. And we either compute the log likelihood privately, or can we take the argmax privately. And at least for now, we're going to always ignore this step, and we're just going to always output some k that had the highest log likelihood in terms of our private algorithm. And so fortunately, we do know how to privately compute argmaxes. So here's the report noisy max algorithm that was kind of folklore for a long time until the privacy book, and it effectively calculates noisy approximations for a stream of queries, and it tells you back which query had the largest noisy value. And so you take in queries and you evaluate queries, and you add Laplace noise with parameter that depends on your desired privacy guarantee and on the sensitivity of f. And you then just output k hat that is a noisy argmax. It's very simple, and the nice thing is that although you have possibly m queries, you don't have to pay in terms of your privacy budget for the fact that you have m queries, because really you just care about one thing, which is the query that has the largest value. And so the idea for our offline private change point algorithm is to run report noisy max, these log likelihood ratios as our queries. And so the algorithm goes like this. We have our input database and our privacy parameter, and we still compute the same likelihood ratios. And then for each time point, we draw some noise And this step is actually not critical for the algorithm, but I put it here just to kind of like illustrate a thing that you can do. If you don't care about privacy, then you can still compute this like non-private MLE just based upon like things you have done so far. Obviously, if you care about privacy, don't actually like output this, but this is more just kind of as like a highlight that you can still recover the same like non-private estimator if you want. And then you're going to output KN tilde, which is the like noisy argmax. And so really, this is basically QSUM plus this like same private algorithm. Anybody see any problems with this?
What is delta L?
Yes, good, good. So one caveat here is that we need this to be finite and like hopefully small. And so really, what is delta L, and is this reasonable to assume? So it turns out delta L is this thing. It's a difference between this like biggest ratio and the smallest ratio within logs. So it's nice that we can compute this, but really by assuming this thing's finite, we're actually like restricting ourselves to a class of P0 and P1. And in particular, it implies sort of like a uniform bound on the probability ratios of P0 and P1, and they also have to have the same support. So it's fine if we have particular distributions where this is like a reasonable number. In fact, this does not hold, for example, for P0 and P1 being like Gaussians. So this is certainly not the most general case. Hold off on until 3 slides and I'll tell you how to remove this assumption. And for our accuracy guarantee, we're going to talk about alpha beta accuracy, which is that we want to be within some like additive alpha of the true change point with high probability. Okay, so here's our main results. So this offline algorithm is, first of all, differentially private, yay. And if we have this assumption, then it's alpha beta accurate for this alpha. And I'll tell you how to interpret that in a second. And this C term is something like the KL divergence between these two distributions. It's not symmetric, and so we have to take the min in both directions. But you can think of C as being just the like KL divergence. Okay, so how should you interpret this term? It's kind of weird, and there's 2 things. And so like an important note is that the like MLE estimate actually has like this accuracy, which is the same as this first term up to some factors of 2. And so really this first term just comes from the fact that we can't do better than the like non-private estimate. And it's actually worth saying that we are the first ones to give even like non-private finite sample accuracy guarantees for this like MLE, which is actually kind of shocking. And I thought that this would like for sure be known, and it turns out it's really because like statisticians and computer scientists have different things they mean when they say the word accuracy. So we are the first ones to give this version of like an accuracy guarantee. Okay, so this is effectively the best that you can do, even like non-privately. And then there's like this term, which can be interpreted as like saying, really, the cost of privacy asymptotically is roughly this kind of KL divergence over epsilon. Because if you compare these 2 terms, so you have like C over delta L squared here, and here you lose the square, but you also gain this extra 1 over epsilon term, and so you're sort of trading off a C for an epsilon here. And so effectively this is saying this is the cost of doing this privately is this term. And the proof idea, kind of in one paragraph, is saying really there's like two things that can possibly go wrong. I might have bad noise and I might have bad data. And by bad noise and bad data, I really mean draws from the underlying randomness that will cause me to think that a change point was at some time other than within this like alpha window of the true change, right? And so if I have like well-behaved data and they're gonna look pretty dramatically different, it's gonna be like, P0, P1. And so we bound that by talking about how far apart are these two distributions. And so that's why this KL divergence term is important because it like helps us bound how likely are we to have samples that actually look very close even though they are drawn from like two different distributions. And the bad noise, I might have like a great data that are very well behaved like this and like this, and then maybe I just get like wild noise draws that make things look like constant all the time. Well, that's pretty unlikely because I would have to get like a bunch of noise draws that are like outliers and don't really look like they're being sampled from this like Laplace, and so we bound that error using some like concentration inequalities on these draws. Okay, and so I promised you how we can handle things if this is not bounded. Effectively, we can run the same algorithm, and we're just going to like truncate our log likelihood. And so before we had this sum, and we're now just going to like truncate it using some like a smartly chosen parameter A. And we're going to like truncate it to be within some range. And the nice thing is that now delta L is just A because they have insured it. And it's actually not so different than if you're doing private deep learning and you want to clip gradients, and kind of like in the worst case, they can be very, very large, but it actually helps you doing it privately to do that clipping.
Can I just say one? Can you remind me? Are you adding noise to L, or are you adding noise to each sum n?
We're adding noise to each L.
Okay.
Yeah.
Because the variance isn't really constant as a function of k, right? So, is it practically make sense to? That is to say, when k is n, there's one term. When k is 1, there's n terms.
Yeah.
And so.
It's a good question that I'll have to think about more about, like how the variance looks as you.
Because this is a problem they run into a lot in change point, right? Is that you normalize things because the variances are always different in some way. Okay.
Yeah. It was actually shocking, is we expected this clipping to really harm accuracy because effectively you're like throwing away information, and that might be very important. But it didn't at all, and in fact we found that in like a lot of cases you actually want this A to be just like very, very small, because in like a lot of cases knowing even just like the sign of this has like enough information. Is it positive or is it negative? And so that was like pretty surprising. And so kind of the like miracle of this is if you run the same algorithm and you just plug in delta L A instead of L, then like the same algorithm works and you actually get the same privacy guarantee and the same accuracy, and you just swap out delta L with A. And this was in fact like very surprising to us. And it may be like related to that point. Any questions on this?
Can you say again how you measure accuracy here?
So this is with probability 1 minus beta, I'm going to be at most an additive alpha away from the true change point. And so here, if you do this like on truncation, and like the exact same thing will work, you just swap out A here, and the same bound holds. And it also holds here too, if you.
The bound is with respect to the truncated function?
So there's a true change point time k star, and we're going to produce some like a private estimate k tilde, and we want the like absolute value difference between k tilde and k star to be at most alpha with probability 1 minus beta.
So what about if there's no change point? Because this is usually the first question, right? Is there a change point? So is it above some threshold? And then if it is, where's the change point?
Yeah. So here we assume, in the offline case, we assume that there is a change point, and this will make more sense as we move into the online setting, where you're first going to like test if there is one, and then if there is one, then you'll call this one as a subroutine.
I mean, even in the offline case, it still makes sense to ask, is there a change point, right?
Yeah.
That is reduced to a hypothesis testing.
So yeah, but you still would want to do it privately in some sense, right?
Yeah, so just to interpret the accuracy guarantee, so whenever alpha is smaller than 1, so this is saying that the probability of correctly detecting the change point is 1 minus beta. Because you're talking about index, right? So
Yeah. This alpha shouldn't be smaller than 1.
I mean, you could if C is, oh, okay. Okay.
Yeah.
Delta L is also.
Yeah. So I want to also compare this to a paper that came out about the same time, and we have a few of the like authors here. I'm trying to like map first names and last names. Clement, Gautam, Adra, Adam and John. And this was in like Audra's talk on Monday. And so if you were here, then you saw this talk. If not, it's recorded. And it's a great paper. And so this was done around the same time and came out probably like a couple months after ours. And so they also solve the same problem, private change point, but they do this using algorithms that they developed for private hypothesis testing, and they effectively have like a reduction between these two problems, saying that you can use these algorithms to solve this problem. And to be like really like a high level, both algorithms are like effectively doing the same thing. They both modify the true distributions in some ways, and the accuracy depends on some distance measure between these like modified distributions. We have different modification tools, and we use different like distance measures, but kind of had like a bird's eye view, like effectively doing the same thing. But because of these, because of these differences, you can't really compare accuracy across one or the other without knowing like specifics of the exact distributions. And I will say, in like an overly stylized model, that is really not fair to kind of like either paper. Ours is better in the case of a large change, but theirs is better like I'm finding small changes. But again, I want to like emphasize this is like an overly stylized model, and it's not like a blanket statement, and you really have to kind of like look at the like exact accuracy bounds on the particular distributions to make an exact comparison. But they're kind of like more in the same vein. Any more questions about the offline stuff? Yeah.
So do both papers?
How do you know if there's a change?
Yeah, no. But do both papers assume that P1 is, or whatever the alternative is some fixed, probably like fixed model? Because usually with the change point, if there is a change, you have to still estimate the models. So
Ours does. I don't know. Got
So-
yours.
We also have a model where it starts off as a fixed distribution and then changes to something which is far, but with the caveat that it has to be, say, a discrete distribution and you know the size. It's kind of a reduction from like goodness of fit testing to change point detection, if that makes sense. You can probably do this for, given a sort of goodness of fit style algorithm, you can plug it into our reduction and it'll still give you something. If that makes sense.
because the typical change point is that there's a change, but I don't know the underlying models, right? So they still have to be fit. So usually it's ratios of like maximum likelihood estimators and things like this. I mean,
Hold off until my very last slide,
okay.
and then we'll discuss. All right, so for this online case, so this is strictly harder because you have to find the change quickly without very much post-change data, right? Because if you like wait a long time and you like collect more data, then you're going to be too late and the change will have like happened a long time ago. And so the approach is going to be to first privately like check if a change occurred, and then once we have a change, then we're going to run our like offline algorithm on that paper. We're going to check by looking at like a sliding window of size n, and I'm going to ask, do I think a change occurred in this window of the last n points? Fortunately, we like also have a like a private algorithm for this, and so again, thank you to the privacy community for making great tools in the past decade. And this algorithm is the like above noisy threshold algorithm, which is effectively what lives beneath sparse vector. And so this is a like a private algorithm for like finding which queries in a stream have an answer above a given threshold. And it works like this. And so it takes in some like input database and a stream of queries and sensitivity bounds, privacy parameter, and some threshold t. And we're going to first noise up our like threshold, and then for each query, we're going to sample applause, noise again, and we're going to check if a noisy answer to that query on the data is above like a noisy version of the threshold. Then I'm going to say it was time I, and halt. And if not, then we're going to say at time I saw no change, and then we'll continue in this loop. And so effectively, it just tells you what is the first time at which the like noisy answer of this query was above a noisy version of our threshold. Okay, so actually here's how we're going to run our first step is we're going to run above noisy threshold on these partial log likelihood queries in a sliding window of size n. And so this is our like online algorithm, which is basically doing these two things. So we take in database privacy parameter threshold, noise up our threshold, and for each data point, I'm going to compute Lj, which is the maximum of the log likelihood ratio of the last n points. And so really this is saying how likely is it that I think a change occurred in the last n points. And we're then going to like add noise and check if the noisy answer to this query is above our noisy threshold. And if yes, then we're going to run offline algorithm on these last n points. And we're done then, And if not, then we're going to keep like going back, and we'll just continue this loop until we find some point at which we think a change occurred.
What is n?
Huh?
What is n?
N is a parameter that you can choose. Alternatively, think of it as the size of the data that you start with on the first day. And so if you have some past database, and then like tomorrow, then you'll get one new point, and then you can slide one. And so it's either your choice or it's a constraint based upon how much data you have at day one. All right, and so here's the main result in the online case. And so it's epsilon differentially private. Again, we're in this case where we're going to assume delta L is like bounded, and you have some smartly chosen threshold. Then it's alpha beta accurate for this alpha. And a few things to say before we like interpret this thing. So our C parameter is the same KL divergence. How do we choose these thresholds? In the paper, we have like exact expressions of these. They are really big and really ugly, and so if you think this is a bad expression, wait until you see our T's. But effectively, this is a constant, and this is something like order n, and so you like shouldn't be concerned about this being like an empty set. Okay, and so back,
Order T?
order n. N is the size of your window. What is T in your question?
Like capital T, the size of the entire stream, the one that not...
T is your threshold, not your stream size.
Oh,
Yeah. Yeah. And so in fact, your stream can be infinite as long as your change point time is at some like finite time point. Yeah. Okay, and so this actually looks extremely similar to what we had before. And so this is great news. We have only lost some factors of 2 compared to the online, or like compared to the offline case. And so really this says, in fact, don't lose anything aside from some constants from being in this like much harder environment. And of course, this can also be done without this like assumption. We just used offline, non-truncated as the thing that we call once we have found a window. You can do the same thing and just call this like truncated version, and it will qualitatively be the same. We haven't done the math. Maybe you lose an extra like factor of 2 or something, but it will be effectively the same thing. And I think like an important thing to note in both of these, both in the like online and in the offline case, is that there is like no dependence on n. And this is less surprising in the online case because this n is like just some kind of like internal parameter, but it's more surprising in the offline case because it's saying that your accuracy is going to be constant no matter how much data you either do or don't have. So I'll give a few more like hand-wavy proof ideas. And so for like privacy, it's actually very straightforward. We give like half our privacy budget to the above nosy threshold, and we give half our like privacy budget to this like offline algorithm, and we compose to get overall epsilon. And this is where our sort of like factors of 2 arrive, is because we are losing them in this case because we split. And for accuracy, it's a little bit more detailed. So we have 2 things that can go wrong. We might fail to pick the right window, and we might also fail within the correct window after we have chosen it. And so we have beta over 2 failure probability for this like window choice. And again, there's kind of like two things that can go wrong here. We might raise the alarm too early. We might pick a window before a change point occurred. And so that's the role of this TL, is making sure that our threshold is going to be high enough to have a low false positive rate, because we have to have some value above TL, and so we have to have sufficient likelihood of a change occurring. And so we bound it with this term. And we also can't fail to raise an alarm at the true change. And I don't want to pass a change point, because then I will have missed it. And so that's the role of this TH, which is making sure their threshold isn't so high that you might fail to raise an alarm even when a true change occurred. And so these two things ensure that with high probability, we're going to find the correct window. And then we have this beta over 2 failure probability for being more than alpha far, conditioned on finding the right window. And so this is conditioned on not being in this bad event. I now have to find the correct change point within that window. Fortunately, we already have an accuracy theorem that ensures that with high probability, we're going to be in the right window. And then we just take union bounds over these two things. And so here we lose a couple more factors of 2. And so there's where all of our missing 2s came from. Any questions on my very hand-wavy proof ideas? I even called them ideas because I feel it isn't even a real sketch yet. It's just a vague, it's a cloud dream of a proof. Okay, and so someone asked about multiple change points. A few people did. I think actually this is kind of a nice kind of meta point, which is that in statistics, this is a really hard problem. But at the same time, in privacy, our sparse vector can be very easily extended to find multiple above threshold queries. And so I told my statistics co-authors, I think that we can do this. It's really straightforward. And they're like, no, and that's way too hard. It's definitely going to be its own paper. And I'm I don't think so. And in fact, because of sparse vector, it really is just the same as running M sequential instantiations of this single change point. And so I feel this is kind of a meta, almost like a proselytizing what it's working across fields. Is that really, it's not we did magic here in the math, but rather we saw there's these very powerful privacy tools, and they can be used to solve a problem that is hard without these privacy tools. And so we applied it. And in fact, it was I don't want to say that it was super straightforward, because of course there's a bunch of math details, but really we just noticed we have tools to solve an existing hard problem, and let's do that.
So in this case, do you assume that there are 2 different levels and jumping from here to there multiple times within the N sequence?
So here we're going to find M change points, and they can be points being drawn
because then
from M plus 1 different distributions.
Oh, okay.
And so don't think of it as things being drawn from a level, but think of it as a points being drawn from these different distributions.
But then your L, definition of L, how does it change?
Hang on one slide. Yeah. Okay. And so first I'll tell you what our main theorem is. And it really looks exactly the same. We just have some additional factors of M in our log. And so really the only change in our loss is just this log m, and this comes from doing a like union bound over these m like sequential change point problems. Some like important details, because I don't want to say that it was just kind of like an immediate application. In fact, there was a lot of math under the hood. So we have to reset every time our like thresholds and our delta L, because we're having different distributions every time. And so you have to reset these like you would for a single change point between time I and time I plus 1. And we also can't have these change points being too close. They have to be at most n apart. And this kind of makes sense intuitively, right? Because if I have too few samples from one distribution, that might just look like a few outliers being sampled from like the previous distribution. And so like intuitively it makes sense that we need some bound on these being like sufficiently far apart. It turns out that we also need this algorithmically because we're going to wait n points after we have like identified a like change point to estimate before we restart the like algorithm. And so in this picture, imagine this is like time here, and say there's some like a true change point k star I. And so things before this are sampled from one distribution, and things after this are being sampled from like a different distribution. And we found some window here of size n, and we called offline change point, and we output k tilde I here, and we found this. And so then we're going to wait until we have accumulated n more points before we're going to start our next window here. Why do we do this? For two reasons. First, because we don't want to reuse data from the previous window. If we started just right here, then kind of like these points are going to be used in both windows, and then we have some kind of like complicated conditioning happening, and we can no longer claim these points are actually sampled IID, but rather they are sampled from the distribution that would cause us to identify this as a change point, and that's complicated to sort of like reason about, and so we don't want to use these twice. Additionally, we don't want to like accidentally use data from the wrong distribution, because again, if I started my new window here, then I would have some points here that are not actually drawn from PI, but they're actually drawn from PI minus 1. And so that will kind of like throw off our math. And so we wait n points, and then we start a new window. I'll just say kind of like one thing about the empirical results in the paper. So we first find in fact that are like theoretical results appear like empirically as well. And we also ran some like simulations in the case where we had the wrong belief about how the data points are drawn. And so we had the wrong P0, the wrong P1, and the algorithm still seemed to find approximately the right change point. And so that tells us we should try to do theory about the case in which we don't know these exact distributions, which we are currently doing. And so this is joint work with like my two grad students, Yulia and Wenrong, and so with Farah Krabel. And we started out trying to relax the assumption of kind of like one dramatic change point. And we actually thought about like drift. And so maybe points aren't really being sampled IID, but maybe there's some like a smoothly changing distribution. We should be able to like identify and to measure that change as well. And then it turned out kind of surprisingly that these same techniques also work in the case where we don't exactly know the pre-change and the post-change distributions. And so that was kind of surprising to us, but the math ends up being the same. So that's great. And I will say that kind of like a larger goal is thinking about like online learning algorithms that can somehow self-audit for like correctness. And so maybe I have first learned some like classifier on some old data, and I acquire new data, and I want to at some point say my new data look pretty different from the old stuff. I think I need to retrain my like classifier. And like in this past NeurIPS with like Tara Crable and with 2 other grad students at like Georgia Tech, we did this for kind of like worst case adversarial data growth. But of course, if you think your data are not going to change very often, then you can probably do a whole lot better in this like change points environment. That's it. Thank you.
So I guess we had a few questions during the talk. So maybe since we're running a little late, maybe we'll hold further questions until the break.
Yeah, sure.
Thanks.